Welcome to Math 2318, Section 5.4. In question 1 here, we have a basis B with B1, B2, B3, and a basis D, D1, and D2. T is our linear transformation going from V to W. In V, we have B1, B2, B3, and in W, we have D1 and D2. So what do I know? I know that T of B maps into minus 8 minus 1. They gave us that there. T of B2 maps into 8, 2. And T of B3 maps into minus 3 and 0. And so if you put that together, that gives us our matrix for T relative to these two bases. So just put in the columns for what T does to B1, B2, and B3. Alright, in question 2, we have E1, E2, E3 are the standard basis for R3. B1, B2, B3 is a basis for the vector space V, and T goes from R3 into V. Now, how does it do that? Well, T of x1, x2, x3 goes into this particular computation. So here's just a graphical map of what T is doing. Now, what does T do to E1? Well, E1 is 1, 0, 0. And so if you put that into our formula, all right, you got 0 minus 0, 1 plus 0, and 0 minus 1, which tells me what T does to E1 relative to the new basis in V. And so I repeat that process for T of E3, just putting in E3, tracing through what does it do, putting in E3, 0, 0, 1, looking to see what does it do, and then that gives me my particular matrix of T relative to E and B. In question 3, we have a mapping, and the mapping takes an element in P2, second degree polynomials, into the second degree polynomials, and it does it in this particular manner. They're showing us what it does to this second degree polynomial. Okay, we get this combination, and they want us to assume the map is already linear. So what does it do relative to the normal basis? Well, all I have to do is take our formula, put in the normal basis. So T of 1, okay, that's my normal basis. That's 1, 0t, 0t squared. Trace through what happens in the formula, and that goes to 5, 7, and 0. There's no t squared part. And then repeat the process for what it does to t. Well, t is 0 plus 1t plus 0t squared. Alright, so we trace through what does that do, and that gives me 0, minus 3, and 8. What about t of t squared? Well, then that's 0 plus 0t plus 1t squared. Alright, so again, tracing out each of the pieces and what that happens, that goes to 0, 0, 1. So putting all that together, we get the matrix for that particular transformation, and it's just what it does to the standard bases. All right, in question 4, we have t going from P2 to R3. And it does it in the following way. T of this second degree polynomial is p at -1, p at 0, and p at 3. So, what does it do to this particular p? P of t is -2 plus t. Well, it's going to be p of -1. So I plug in -1 and I get -3. P at 0, I get -2. P at 3, I get -2 plus 3, which is 1. So that's what it does to this particular polynomial. Now they want us to prove that it is a linear transformation. So what does it do to a sum? Well, t of a sum would be p at that point, q at that point. And so normal operations of functions that can be split up, and that's just t applied to p of t and t applied to q of t. Now, what about for scalars? Well, let's see, t of c times p of t. Well, then that would just carry over into the process of c times that polynomial. And so it can factor back out and no problem. So this is a linear transformation. Now, what does it do to the standard basis of 1t and t squared? Well, 1 is the constant function 1, so it doesn't matter what you plug in, you only get out 1. T of t, okay, well t is the identity, so if you plug in -1, 0, and 3, that's what comes out. And if you apply it to t squared, it's -1, 0, and 3 squared. And so our matrix relative to the standard basis looks like the following one. All right. They want us to find the B matrix for the transformation x goes to A times x, where the basis is B1 and B2. So we do this by an example that was shown in the textbook. We form P. The matrix P is just B1 and B2. All right. And now I need to form P inverse. Now, if you remember, there was a fast way to do this. I need 1 over the determinant. So let's see. That's -1 minus a -2, which is a +1. Okay, so I don't get anything from 1 over the determinant. And then to find it, we simply switch the diagonals. Okay, so the -1 down, the 1 up, and then we take a negative of each of the other diagonals, so -2 and 1. And so to get it, we're going to form P inverse AP. So first off, I did A times P, so here's A times our P matrix. All right, did that. So now I take P inverse multiplied by that result, and so that gives me my B matrix for the given transformation. So not too hard because it's only 2 by 2 matrix. All right, question 6. We are given matrix A. We are given B is B1 and B2, so they're given there. T is a mapping that is going from R2 to R2. They want us to verify that B1 is actually an eigenvector, but B is not diagonalizable. and they want us to find the B matrix. So let's look for the eigenvalues. So I form the determinant of A minus lambda I, so we do that, minus a minus 9. All right, so multiplying this process out, I end up with, once it cleans up, lambda squared minus 2 lambda plus 1 is 0, which factors into lambda minus 1, and I get lambda is 1. So I only get one eigenvalue, but that's not terrible because it might have two eigenvectors. But let's see. So I form A minus I, because lambda is 1. And so let's see what happens. So we do that, A minus I, so subtract 1, and I get this particular matrix, but I can easily divide the first row by 3 and then add it to the second row. And so what I see is x2 is free, x1 is just x2. So I really get x2 times 1, 1. So I only have one eigenvector. That's not enough, so I can't diagonalize A. Alright, so they wanted us to find the B matrix for the transformation. Alright, so here's P. Alright, the determinant is 2 minus 1 is 1. I can easily find P inverse, swap the diagonals, take a negative of the other diagonals, and now I find A times P, and then P inverse times AP to get the B matrix for the transformation. Now in this last part they actually stepped through it for us, but we already did all of that, so there's nothing particularly new there.